Swayam Prabha. Digital India. Educated India.
Okay, so welcome to the next class of this course. So far we have completed the first part of this course, which is the kinetic theory of gases, and today we'll start a new topic, right? So which is called thermodynamics. Okay, so thermodynamics. So far what we have been doing is we have been looking at matter from very microscopic perspective, right? So we started with the assumption that matter is made up of many molecules which are dimensionless, and we made some drastic assumptions, and we calculated the emerging properties like pressure, temperature, and also like non-equilibrium transport properties like viscosity, thermal conductivity, diffusivity, and so on, right? But it turns out, like we discussed in the last class as well, there are limitations to that approach, right? The biggest one being we have to make a lot of assumptions at the microscopic scale, right? So therefore, in that sense, it's like a bottom-up approach, right? The kinetic theory was like you start from the microscopic view and you infer the macroscopic properties. But on the other hand, thermodynamics is like an opposite approach, right? So it's like a top-down approach where we completely ignore the microscopic details of the system, and the starting point of this formulation is basically the macroscopic variables, right? So maybe I can write a few things about it. So basically in thermodynamics we start with macroscopic property or macroscopic variables like pressure, temperature, volume, density, and so on, right? So this is where we start, and we completely ignore the microscopic details. Ignore microscopic details. So this is to say that if you give me a system with certain temperature and pressure, I understand that at the microscopic level the system is very chaotic. The gas molecules or molecules of the system, they are moving randomly, they are undergoing collisions, and so on. But in thermodynamics, the basic approach is that we do not really care about what's happening over there, as long as our system shows some steady properties like pressure, temperature, volume, and density, and so on. All right. So this is basically this basically what this approach is all about, right? Right. And also like, and this also offers one of the advantage that we don't really have to make any sort of assumptions about the molecular dynamics. All right. And we will see that in thermodynamics we basically come up with what's known as laws of thermodynamics. So use laws of thermodynamics which are applicable to all the system, right? Which are applicable to all systems, and we use these laws of thermodynamics to infer physical properties of systems, right? So to use laws of thermodynamics to infer physical properties. Okay. So we'll see as we go along in this course how we actually do that. All right. So before we really get into it, there are certain definitions which are important to go through. Okay, so we'll use various words in this formulation of thermodynamics. So let's go through them one by one, right? So definitions. Okay. So perhaps we can start with what's known as a system, right? So actually I have used this word many times, but let's formally define it. So what is system? Okay. So basically system is a So system is a subset of universe which is under observation. Right. So basically, maybe I can draw it. I have actually drawn these things many times. So usually I always draw a box containing some molecules, right? Many molecules, and I usually also draw a boundary, right? Something like that, and simply the definition of system is okay. So that this entire space is the universe, but whatever we are interested in, whatever so there is a subset of this universe which we are interested in calculating the properties, that is system. It's fairly simple. So this everything that lies inside this wall is known as system, right? And everything outside, like everything on the whole was universe, and everything outside is basically rest of the universe, right? So basically in that sense I can just call my system equals universe minus rest of the universe, right? So whatever remains is our system, right? And you can see that I have drawn a certain boundary, right? So there is a wall, there is this line which separates this system from rest of the universe, and this thing is known as boundary, right? So basically boundary, the partition or the wall that separates system from the universe, from the rest of the universe. Okay, very simple. All right. And depending upon the properties of these walls, okay, so these walls can have various properties, right? They can either be insulating, they can either be conducting but closed, they can either be leaking, and so on, right? So depending upon that we can have various categories of systems, right? So the first one being an isolated system, right? An isolated system is where the gas molecules, they do not really lose any energy, right? Not gas molecules, but any collection of these molecules, when they collide with these walls, they don't lose any energy. So total energy of the system does not change, right? So so an isolated system is when the energy, the system energy remains constant, remains fixed, right? So that is known as an isolated system, and I usually denote, I usually draw schematically as like some dashed lines. Okay. So the other definition is what's known as closed system. Okay, and closed system is where these walls, so the system can lose energy, but it cannot really leak out any particles, right? So this is closed system is basically happens because of a sealed boundary, right? So this is sealed wall, and in this case the volume remains constant. And on the similar lines we can define third thing known as open system, right? So imagine I break this wall and there is a leak in it, right? In which case the system can lose particles as well, molecules as well. In which case there is quantity which is known as chemical potential that remains, which we'll come to that anyway. Okay, so this is like leaking wall, right, or leaking boundary, and in this case mu, which is the chemical potential remains fixed. Okay, so depending upon what kind of system we are interested in, right, and so we can think about the kind of boundary that separates that particular system from the rest of the universe. All right, so that was the first definition. So the second definition is what's known as thermodynamic variables. Okay, and sometimes they are also known as state variables, and also functions of state. Okay, and these are basically all the macroscopic variables. So like macroscopic variables like temperature, pressure, volume, density, viscosity, and so on, right? So all these variables which are basically kind of emerging properties, right? So and like I said, so this is like the underlying concept of thermodynamics, that we are not interested in microscopic details, but this is the starting point. And if you give me a system which is at a particular temperature or pressure, that is my starting point, right? So if you give me two systems which have same pressure and same temperature, I do not really care what so what kind of underlying microscopic dynamics is going through, right? So since we went through kinetic theory, so we can imagine how chaotic the dynamics is at the microscopic scale. But I am only interested in these thermodynamic variables like temperature, pressure, density, and so on. Okay, and these are known as thermodynamic variables. And depending upon what we have, so we can like divide these variables into two more categories. The first one is known as extensive variables. And these are the variables. So variables which are proportional to or which scale with the system size. Okay. So it's like okay. So the simple examples are like total energy, right? So energy, which is typically denoted by symbol U, volume, right, mass, etc., right? So all these variables, you can see that they scale with how many molecules we have in the system, right? So energy of the molecule is like total kinetic and potential energy of those molecules. Similarly, volume, if you increase the number of molecules in the system, the volume will increase. Similarly, mass will increase, right? And the opposite of that is known as intensive variables. Okay, and these variables are basically independent of system size. And examples basically are temperature, pressure, density, etc., right? So it's like saying, so the temperature of this room is not very different from temperature of the Mumbai city, right? So the temperature is that intrinsic or intensive quantity, intensive variable, which is independent of the size of the system that we are interested in. Similarly, pressure, right? So pressure inside this room is also at 1 atmosphere and outside this room is also 1 atmosphere. Similarly, density of these gas molecules is also does not depend upon the size of the system. Okay, so such variables are known as intensive variables, and it often turns out that intensive variables are usually they are more useful in thermodynamics than extensive variables, and we often convert extensive variables to intensive variables by just dividing by the total number of molecules or number of moles of the material that we have. All right. Okay. So the third definition is known is thermodynamic equilibrium. So, so system is said to be in thermodynamic equilibrium when its thermodynamic variables do not change with time, right? So when thermodynamic variables do not change with time. Okay, so it's like saying if I give you a container of gas and I fix and you observe it over some time and the pressure and temperature of that container does not change, you can say that this container is in thermodynamic equilibrium. So, but we should always like keep in our mind that at the microscopic scale the reality is molecular, right? So the molecules are always colliding with each other, they are colliding with wall, and in fact if you now think about it, the instantaneous pressure at the wall also fluctuates all the time, right? So remember how we defined pressure, it was like a molecule hitting the wall and transferring its momentum, right? And this is an entirely random process, right? At any given point the number of molecules that are hitting the wall and transferring momentum, that fluctuates hugely, right? But we are not interested in those fluctuations, and we are not even interested in what is causing that pressure and temperature, right? But as long as those quantities are do not change with time, we say that it is in thermodynamic equilibrium and we are happy with it. All right. And similarly pressure, density and so on, right? So all these variables, if they do not change with time, then system is said to be in a thermodynamic equilibrium. All right. So and next thing is known as thermodynamic process. Okay, and simply put, so this is just a process process of transitioning from one thermodynamic state or one equilibrium state to the other, right? So it's like saying I give you a container which had a certain pressure and temperature, for example, at given point. Then I did something to that system. Maybe I brought a candle close to it, I heat it, I leaked some particles out, whatever, and I let that process finish, and and the system goes into another state with certain temperature and pressure, right? And that entire process that between those two states is typically known as thermodynamic process, right? And the other definition is basically what's known as indicator diagram, right? And we have actually used it already, right? So if you remember from the last class, 2 classes before, we were discussing about Andrew's experiment, right? And what we were basically doing was, so we prepared our system and we varied temperature, and then we varied so basically Andrew varied the temperature of this collection of carbon dioxide molecules, and he varied the volume and measured the pressure and so on, right? And what was going on was like this system was transitioning from one thermodynamic state, right, to the other equilibrium state. So first state was denoted by P1 V1, the other state was denoted by P2 V2, right. So and we often and this is like typically a thermodynamic process, right. So the definition that we defined before. So this is like a thermodynamic process where system is transitioning from one equilibrium state to another equilibrium state, and it can often be indicated on what's known as indicator diagram, which is a plot between two thermodynamic variables, right. So in this case, pressure and volume, right. So basically indicator diagram is basically plot between two thermodynamic variables. Okay, and a few more important things regarding this. So when we say that the process has undergone so there is a thermodynamic process which takes you from state 1 to state 2, right. So and I very conveniently joined these 2 points with a solid line, but it has far reaching consequences in thermodynamics, right. So when I draw a solid line, that means all the states intermediate between 1 and 2, they are also in equilibrium, right. So what I mean is, like, say I change the volume of my system, right. So say I start with state 1, I suddenly change the volume, and of course the pressure will also change. Say I am doing it at constant temperature, and I let this system evolve to another intermediate state and let it go to that equilibrium state, right. So I wait long enough that there is so that all the intermediate states, they are also in equilibrium. Okay, so basically maybe I can write, so solid line connecting two equilibrium states in the indicator diagram. Represents what's known as a reversible process. Okay, there's another definition. And reversible process is such that all the states in between two states, so they are also in equilibrium, right. And all intermediate states are also in equilibrium, in thermodynamic equilibrium. Right? And you can also see that for this system to achieve an equilibrium. So remember, what was the definition of equilibrium? So equilibrium is defined as when the variables do not change over time, right. So you take this system to an intermediate state, you wait long enough for this new p and p's and v's to remain constant over a very long time, and then you change the parameters again, and so on, right. So you go through infinite number of equilibrium states, right. And you can now imagine that such a process would be very, very slow, right. So therefore so whatever I defined reversible process, this is also known as what's known as quasi-static process, right. So this process is evolving really, really slowly, right. So that we ensure that our system always achieves all these intermediate equilibrium states. Okay. And when we say reversible, that means we can easily go back and forth between that, right. And that's why and that is basically the meaning of joining these two lines by a solid line. That means your process is quasi-static and it is reversible, and we'll get into these concepts later as well. All right. And say in another case, say I take my system from state 3 to 4, but I do not really care about the reversibility, right. So I do not really care about whether the intermediate states were also in equilibrium, right? In which case we basically join these two points by a either dashed or solid line, right? So basically a non quasi-static or irreversible process is represented by a dashed line. Okay. So few things to worry about. Okay. So most of the times we will be actually working with reversible and quasi-static processes. Okay. Let's move on. So the next definition is basically concept of heat and work. Okay. So we have actually defined this before as well, especially heat. So in kinetic theory, I defined that heat is nothing but it is the energy in transit, right? So say so you have some energy in the system and it is traveling from one point to the other, and that transport of energy is typically called heat. All right. Okay. So energy in transit. Okay. And heat is basically, and what is the difference between heat and work, right? So heat is energy in transit. Okay. So so energy in transit when when the volume of the system does not change, right? Volume does not change, but work we define when the volume of the system can change. Okay, another way to think about it is so if there are any mechanical components involved in the system, for example inside our engines, right? So there is a piston. So when you heat up your engine, heat up the cylinder, the piston moves up, right? Moves out, and that motion of the piston can be associated with some kind of work done because there are mechanical components which are moving from one point to the other. But on the other hand, say you have a cylinder which is at certain temperature, and you don't let the piston move, but the energy will still leak out of that cylinder, right, without any movement of mechanical components, in which case that transfer of energy is known as heat. All right. So I hope that concept is clear. All right. So even though we used the concept of heat in kinetic theory little bit, especially when we were talking about the thermal conductivity, but we really didn't have to define a quantity associated with it, because we knew that at the very fundamental scale, both energy and work, both heat and work are basically energy. But since in thermodynamics our so we start with these variables, so it's important to assign some notations to these quantities. All right. So typically we denote heat by a symbol Q and work by a symbol W. All right. So and you can very easily see that the units of both Q, W and U is like the energy, are joules. Okay. So they all have same units. All right. But the only difference now is that we are giving some notations to these concepts, heat and work. All right. And another thing which probably is obvious, that the fundamental quantity here is energy, right? So if say I have this pen, right? So this pen has many number of molecules and they are like jiggling around, they are interacting with their neighbors and so on. So there is energy in this system, right? But I can't really say there is this much joules of work or this much joules of heat in this system, right? That concept gets triggered only when we are thinking about transferring this energy into some other form, right? Otherwise the energy is the fundamental concept, but when we transit that energy from from one point to the other, only then the concept of heat and work comes into the picture. All right. So it's absurd to say that it has so much work or so much heat and so on. Okay. So the next definition is basically heat capacity. Okay. Okay, and simply put, so this is amount of heat required to raise the temperature of the system by 1 Kelvin or 1 degree Celsius, any temperature scale on this linear scale. All right. And so basically what I mean is that, say you have a system which is at temperature T, right, and you add certain heat delta Q, and this system basically goes from T plus delta T. Okay. So you basically heat up this system, right. So you maybe bring a candle close to it and its temperature will increase, right, and then you can define this specific heat which is denoted by symbol C. This is basically delta Q divided by delta T, and the units of this quantity are joule per Kelvin. All right. And you can see that here this specific this heat capacity is actually an extensive variable, right. So if you have a bigger system, you need large amount of heat to raise its temperature by 1 degree, right. For example, your cup of tea, right. So it doesn't require that much energy to raise its temperature by 1 degree, but say you have a pond or lake, right. So lake has many number of water molecules, so it requires proportionally high amount of heat to raise the temperature by 1 degree, right. So what I mean is this is an extensive variable, right, and it is often useful to convert this heat capacity to an intensive quantity, right, which is usually known as specific heat capacity. Okay, and this is denoted by symbol small c, right, something like that, which is capital C divided by total mass of the system, for example, right. So I'm just scaling it with the system, and this typically achieves the units of joule per Kelvin per kilogram. Or you can also define what's known as molar heat capacity, which either you can define by simple Cm or something, it doesn't matter, and that is basically C divided by N. So how many number of moles you have in the system, and this will have units of joule per Kelvin per mole, right. But important thing is that both specific heat capacity and molar heat capacities, they are now intensive variables. Okay. All right. So so this is what this is where we end as far as the definitions, some important definitions are concerned. But now we will basically start getting into the concept of thermodynamics, right. So let us start with this concept that I just defined, which is the heat capacity, right. So I said I give you a system, how much heat is required to raise its temperature by 1 Kelvin, right. And now you can think of it. Okay, so this experiment or this process can be can happen in two ways, right. Okay, so there are two possibilities. Okay, so the one possibility is where okay, so remember what we are doing is we are our aim is to increase the temperature of this system. So you have T and I want to increase its temperature by 1, right, or by certain amount delta T by supplying heat delta Q, right. So I can do this process either by supplying heat at constant pressure, or I can do this protocol by supplying heat at constant volume, right. So and this can be basically written as, in this case the specific heat is denoted by Cp, where the subscript P denotes that process happens at a constant volume, and in this case the specific heat is defined as del Q by del T at constant pressure, right. And in this case this is Cv, which is del Q by del T at constant volume. Okay. And now I will draw a few few simple diagrams to understand what this process is actually, how it looks like. All right. So just imagine that we have a container which has some, say, gas molecules, right, and there is a piston, there is a ball attached to a piston which is kept at certain constant pressure, right. So what we are doing is we are supplying some heat delta Q, and we are interested in raising this temperature from T to T plus delta T. Now you can now again, if you go back to the kinetic picture of matter, right. So when I supply heat to this system, the kinetic energy of these molecules will increase, right, and therefore the temperature will increase, but some amount of that energy will be utilized in moving this piston outwards, right. So the piston will move, right. So since we have kept the pressure constant, right. So so in this case maybe I can write part of heat wasted in moving the piston, right, which is attached to a load which is creating some pressure P. But on the other hand, okay, so here P is fixed, right, so this is P fixed. But on the other hand, if I do the same experiment, right, but I let the pressure vary, but I keep the volume of the system constant, right. So if I don't let the volume of this system change, in that case the piston can't move outwards, and all the heat that I am supplying into the system, that solely increases the temperature of the gas, right, temperature of the system. It does not really gets wasted in doing any external work, right. So so therefore piston does not move. So and all the heat gets utilized in raising the temperature. Okay, this is very simple, and I want you to just think about it, right. And therefore we can conclude that the amount of heat required to raise the temperature of a system which has fixed volume should be lower than the amount of heat required to raise the temperature of a system where pressure is constant and it can do work on it, right, because there is wastage of heat. So therefore using this concept we can infer that Cp is always greater than Cv, right. Okay. And we'll actually get into this, right. So we'll actually derive the expression of what is the difference between these two heat capacities at constant pressure and volume, right. But yeah, so still it's a nice way to think about these systems from a kinetic perspective and drawing some conclusion about the thermodynamics. All right. Okay, so the next thing that we'll basically do is, which we have already touched upon in kinetic theory, is first law of thermodynamics. Okay. All right. And the underlying assumption of this first law is that, okay, so what is the underlying assumption? Is that the total energy of the universe remains constant, right. So this is the most important assumption that underlies the first law of thermodynamics, which means that once we were given a universe, its total energy has not changed, right. You can question it with it's totally okay to question this assumption, but it seems like it works fairly well, right. So that whatever universe we are living in, its energy does not change, all right. So in which case, basically this is also known as conservation of energy, conservation of total energy, right. And now in this so keeping this in mind, now we will see what is the formal definition of first law of thermodynamics when applied to a thermodynamic system, all right. So say you are given certain system, right, and it has many molecules, and these molecules, they have lot of kinetic energy, they have potential energy, right. So therefore there is total energy of the system, which we define as internal energy, all right. So internal energy, which is denoted by U, and basically this is total energy of the molecules, which is basically sum of kinetic energy and potential energy and so on, all right. So the total energy of any system, for example this pen, the total energy contained inside this pen is the total, it's known as its internal energy, all right. So now basically what is the first law? So let's apply this first law to this system, right. So according to first law, okay, so statement of first law or first law applied to a thermodynamic system. Okay, so let's say I supply certain heat to this system, so heat, right, and that heat will partially increase the internal energy of the system, right. So maybe in form of kinetic energy and so on, and some part of this this heat will be utilized in doing certain work, okay, and that's it, right. So let me write that statement first. So so first law of statement when applied to this looks like this. So change in internal energy, okay, of the system, that is equal to, so this quantity is equal to amount of heat supplied or removed, okay, it can be anything from the system, plus amount of work done by or on the system, okay. So the total energy of this system at any given point is basically just sum of the change in heat or heat supplied or removed from this system and the amount of work this system either does on the universe or done by universe on this system, okay, and that's it, right. So total energy is just sum of these two properties. So this is basically the first law of thermodynamics, and in terms of notations, so I can just simply write that this change in internal energy delta U is basically change in the heat supplied or given to system plus the amount of work done by or on the system, all right. And usually it is also denoted by differentials, and sometimes you just write Q and W. In other books you can even see this different notations, right. And I will basically talk a little bit about it, right, what is the difference between these notations. So the point here is that so and in fact some other books also write dq plus dw, Okay, so the point here is that, but these are all the statements of first law. All right, so these are all first law. Okay, but just different notations, and different books use different notations. And I'll maybe talk a little bit about why that is the case. All right. So remember, so like I said, the most fundamental quantity in thermodynamics is the total energy, right? So on the other hand, heat and work, they are not really fundamental, right? So they are protocol dependent. So let me give you an example, right? So say I have a ball which is kept at the floor, and I raise it to certain height h, or let's say I raise it by say height mg z. So the amount of energy that has gone into this system is mgz, right? So that is the change in internal energy of this system. Okay, and if you want to write it in differential form, I can just write it mg times dz, right? Something like that. And if you think about it, the internal energy is, like I said, it's a state variable, right? So it just depends upon the fact that so the energy of this system at this point and this point is always given by this much, no matter how I do this process, right? So either I can just pick this ball and keep it here simply, but I can also pick it, toss it around, throw it out of the window, take it back to the room, and so on, and keep it here, right? What will not change is the delta u or du, right? Because that is just the function of dz. But the amount of work that I have done in order to move this from this can be anything, right? I can just either keep it like this, or I can toss it around and keep it like this, in which case the work done will be very different, right? So therefore, in that sense, we can't really, so these q and w's are not really state variables, right? So they are path dependent, they are protocol dependent. So therefore, these are not really exact functions. So it doesn't even make sense to define an exact differential corresponding to these two quantities. Okay, so therefore some books don't really put any d in front of it, because it's absurd to define a differential of work or differential of heat. Or some books just they put this cross on d, just to remind you that this is not really an exact differential. But on the other hand, there are some books which don't really care about it, right? But at the bottom of but at conceptual level, you should always keep in mind that heat and work are not really exact differentials, right? So basically, u is a state function, q and w are not. So therefore, du is defined. On the other hand, dq and dw are not defined. Okay, so keep that in mind. So I think in this course I will always try to put a cross sign on in front of whenever I use dq's and dw, just to remind you that they are fundamentally different from any state variable. All right. Okay, so so the one last thing that I can do before we end is basically, okay, so so remember the statement of first law that we wrote was okay, let me write the first law again. Right. So according to first law, the change in internal energy is basically change in heat plus change in work done, change in work, right? And what about the signs, right? So I am using plus signs in front of every this quantity, right? And there are certain conventions that are used in thermodynamics. Okay, so maybe like signs, maybe I can go to the next page. So signs of delta u, delta w, delta q. Okay, okay. So So every time, okay, so say we have a system, and if its internal energy increases, right, so delta U is positive if internal energy of system increases, okay. Delta U is negative if internal energy decreases. Very simple. But what is more important is that we call delta Q to be positive, okay, if heat is supplied to the system. Okay. So if the system is gaining heat, if we are transferring energy from outside to inside, right, in that case we will say that delta Q is positive and heat is supplied to the system. But in the other case, if delta Q is negative, that means heat removed from the system. Similarly, if delta W is positive, right, delta W positive means since that positive, so remember the statement is delta U is delta Q plus delta W. So delta W positive means that should contribute to the internal energy of the system, and that will only happen if the universe is working on the system, right, if you are working on the system from outside. So delta W positive means work done on the system, right, and similarly if delta W is negative, that means work done by the system on the universe, right. So these signs are important, and remember, so let us again try to draw that. So say there is this wall which is attached to a piston kept at pressure P, right, and you have a collection of these molecules, and say after some time the volume increases by V plus, let me now use this symbol dV, right, P, right, and in this case you can see since the volume of the system is increasing, piston is moving outwards, so work is done by the system on the universe, right. So therefore when work done by the system, so your dV is positive, right, and remember when I said when work is done by the system, your delta W should be negative. So therefore your statement of first law will basically become dq minus P dV, right, because your dV is positive and we want our delta W to be negative, dW to be negative, so we put a minus sign in front, right. So this is when work is done by the system, and in the other case when work done on the system, in that case your dV will be negative, right, because the volume of the system will reduce. In that case the first law basically reads dq plus P dV, because we know that in this case dV is negative, right. All right. So therefore we have so when the work is done on the system, the amount of change in volume is basically contributes to the energy of the system, right. So therefore there is a plus sign here. Okay. All right. So I think this is a good point to end today's class. So in the next class we will basically apply the first law of thermodynamics to determine, okay, so remember what we started with. So we basically introduced the concept of specific heat, the concept of heat capacity, and we claimed that heat capacity at constant pressure is always greater than heat capacity at constant volume, and we'll basically now apply the first statement of first law of thermodynamics to a particular system, and we'll see whether this is true, and if it's true, by how much, right? So that will do. Okay, so thank you.